Okay, well, thank you for coming out on this rather dismal day. Yes, I'm going to be talking primarily about mathematics applied to real-world problems. Almost everything I say can be applied or can be sort of thought of in terms of pure mathematics done in university math departments and in classrooms with some modifications. But that's not my focus. My focus is on mathematics as a tool used in the world by people in their everyday lives, or by engineers or scientists or economists or whatever. So it's mathematics as a tool in the world, which it always was, even though some of us managed to make a pretty good living by taking it into a small room and thinking about it on our own for many hours at a time. So it's mathematics in the world we're going to be talking about. And my starting point can be really summed up in an op-ed I wrote for the Huffington Post on January 1 last year, 2017, and that was the title, and it was absolutely meant for real. That was not meant to be hyperbole, it was not meant to be a metaphor. It is the case that everything I spent my life doing until I was 21 years old, when I graduated from King's College London with an honours degree in mathematics, all of the procedures and methods that I learned in that period have become irrelevant, obsolete in terms of what I do for my living and what other people do. It was late coming, but eventually the field of mathematics succumbed to the rise and the advance of technology. And as in all other walks of life, like the newspapers and the music industry and whatever, it changed completely the way it was done. It's no longer done in anything like the way it was when I grew up and I spent most of my career. It's been very dramatic and it's been powerful and significant. And the poor math teachers around the world are struggling to try to catch up with this, and it's going to take a long time to make that adjustment. But the world moved on around 1985 to 1990, and it's just not going to go back to the way it was. Okay, so by obsolete, I don't mean to say that mathematics itself is irrelevant. It's more relevant now than it's ever been in history. We live in a world created by mathematics. The mathematics still has to be done. It's just done in a very, very different way from the way it was done for most of my career and for thousands of years. This is a revolution that's unique over the whole history of mathematics, save perhaps the introduction of Hindu-Arabic arithmetic, which began in the first 6 or 7 centuries in India, moved up through the Iraq, essentially through Baghdad, when it sort of grew a little bit and algebra was added onto it, then came into Western Europe in the 13th century due to that guy, Fibonacci, who I found a few years ago, as it were. That was a big change that changed the way mathematics was done. But that was really the only one. Well, the printing press had some impact, quite a big impact. But the other big change is the one that took place about 20 years ago. Okay, so to set the scene, let's just look at the way mathematics arises in the world, because this picture, it needs to be at the back of our minds when we understand what it is that's been going on within the last 20, 30 years. And typically, not just typically, but throughout history, this is how mathematics arises and how it's used. There's something going on in the world. It could be shopping, it could be some kind of trade, it could be some kind of engineering. Whatever it is, something's going on. For the sake of an example, since we're living in California, let me imagine you want to remodel your bathroom, because that's the main hobby of people in California. We remodel bathrooms. So you want to remodel your bathroom. So that's the real world situation. You then hire someone, a builder, or maybe even an architect, depending on the degree you want to go into it. But you hire someone who knows about doing bathroom remodels. That person comes in and you talk to them, and they take your ideas of what you want the bathroom to be, which is all sort of fuzzy and human, and they turn it into the language of sort of architecture, adjacencies and affordances and what you want in various places. So it becomes somewhat technical. Technical description in the language, let's say, of architecture. The next step is to turn that sort of architectural description into a precise mathematical description of blueprints, sort of geometric drawings, trigonometric drawings, with spreadsheets, etc. So we've gone now from everyday language to the language of a specific domain like architecture. Now we're in the language of mathematics, where you've got spreadsheets, you've got blueprints, trigonometric drawings, measurements. Then that person gets together with a contractor and they start grinding the numbers. So the mathematics is now getting done. Once you've got it in the language of mathematics, you can apply mathematics, and the mathematics is applied. Then you get mathematical results, and based on those results, people come in and they start to work on your house, and it takes 3 times longer than you expected it would do, and it costs twice as much as you expected to do, but eventually you get, hopefully, the bathroom remodel you wanted. The part on the right, going from the mathematical description to sort of solving equations, running spreadsheets, etc., that's what's typically called a mathematical model. A set of equations, spreadsheets, whatever it is, where the mathematics is done. But that picture, that triangle, is the entire history of mathematics, and it's as valid today as it was at any time. So when people say that mathematics, you know, when a kid says, I don't know why this or how this is going to be used, it's because they don't have the big picture in mind. One of the things, the reason I'm leading off with this is what the recent advances in technology have done is they've allowed us to step back and think much more frequently about the big picture. We don't have to get bogged down in the right, because everything on the right-hand side in that triangle, in that box, that is all automated now. And when you automate that, you can step back and think about the whole picture. You can go back and be like Kepler or Newton, who are actually looking at the planets, and the equations were just ways of describing the planets. You know, when mathematics arises, historically, once we've got it, it's taken away from the real world because you have to do the mathematics. That's the part that's changed, and it's a huge change. Let me just give one more example, because sometimes the mathematical models that arise are given names. And one of the mathematical models, or several mathematical models that arose in the history of mathematics, became known as different geometries. Classically, the first one of all was Euclidean geometry, and that was originally a mathematical model. It was a model, the story goes, and it's probably true to some extent, was that every year when the Nile Delta flooded, people's land barriers disappeared, and they had to redraw the land barriers, the land boundaries, and to draw the land boundaries, they invented this method that became known as geometry, from the Greek phrase geometros, from earth measurement, which allowed them to refigure where the boundaries would go. So geometry began as a mathematical model of the spaces we live in. Okay? And we sort of think of that as geometry. That's really the image most of us have in mind when we talk about geometry of triangles, circles, straight lines, etc., etc. That's really the model we have in mind. It's really the image we have in mind. But geometry is an awful lot more than that. Really, geometry is the mathematics of shape. And if it's the mathematics of shape, it means there are geometries for all aspects of our lives, because shape is a huge part of our lives, and most of our brain is to do with visual recognition. So space around us, shapes around us, they can give rise to different kinds of geometries. And in today's world, there are an awful lot of shapes that are very different and more relevant to our lives than the patterns of shape that were around in Euclid's day. You know, in the days when you were building the Parthenon and you were sort of doing land measurements and so forth, then triangles and circles were a big deal. But today's world, we have very many different kinds of shapes, many of which are actually not visible through our eyes, but are visible to us through other senses and other ways of getting at them. And in fact, the real power of mathematics, the reason mathematics comes into being and becomes a big deal, is it allows us to extend our everyday faculties to see things and understand things and reason about things and actually affect things that are completely invisible to our eyes, that have to be visualized through the tools of mathematics itself. As I like to say, mathematics makes the invisible visible. It extends our sensory capacities to things that are otherwise invisible. And to give one example, here's an example of a use of geometry in order to understand something. Not to understand physical space, but to understand social space. And this is a use of geometry that was introduced by an artist, in fact, Tony Robbin, in the 70s. And he used four-dimensional Euclidean geometry to try to visualize life in a multicultural, multiracial, multilingual society. You know, like Palo Alto, he actually lives in Manhattan, so he was based it on Manhattan. And his idea was this. He said, in a city like Manhattan, you've got a very concentrated landmass. You've got a Euclidean space, a two-dimensional or almost three-dimensional because there's these tall buildings. So you've got, say, a three-dimensional space in which are living people from all around the world who speak different languages, dress differently, look differently, have different cultures, different traditions, different languages, different religions. And each one of those differences is another dimension. And so Manhattan isn't just three dimensions, four if you include time, it's maybe a dozen dimensions because you've got all of these other dimensionalities coming in. And just as we can sort of draw two-dimensional maps to understand the space that we live in, the physical space we live in, Robin said, can we use four dimensions in which the fourth dimension, in the fourth Euclidean dimension, represents the way these different facets of life come together. And over many years, he started, and this was all based on an underlying mathematics, he produced works of art that allowed him to sort of, and not just him, but the observers, to understand or try to understand how you can have these different dimensions coming into play with the three dimensions of the spaces that we live in. Okay.
I think we have a misunderstanding about seeing. We think we see the world out there with our eyes and that this process is objective and automatic. In fact, we see with our minds. We go through life doing geometry. You know, Plato said that the gods are always doing geometry. We're always doing geometry. We go through life applying the geometry that we know on our visual world. And if it doesn't fit that geometry, we don't see it.
Okay, that was made in 1997. It's a little clip from a six-part TV series I worked on for PBS called Life by the Numbers. Interestingly enough, that came out in 79. I think it was 80 when the thing came out. It was 6 hours of broadcasting. It was an hour a week for 6 weeks. KQED showed it several times. When that came out in 1980, all 6 hours was up to date. It was all cutting edge stuff. It was brand new stuff. I've used those videos since then in my teaching to give illustrations. In that period from 1980 to about 2005, almost all of those cutting-edge uses of mathematics became obsolete. They were no longer relevant. We had an interesting one about search. How do you search a database? Well, a couple of years later, Google came out and completely changed it, and it was all different. 6 hours of contemporary mathematics as it was used in the world, in the space of 20 years, almost all of it became irrelevant. I can only show this one because it was actually about art, and art has a sort of a timelessness to it, and everything that Tony Robbins says, and it was a 10-minute segment on Tony Robbins' art, all of that is pretty well up to date, although he actually had to develop special technologies to draw the images. Now you can get them for free on a laptop. But that's a measure, if you wanted one, of how fast things have changed. 6 hours worth of stuff, all essentially except for the little historical bits we included, and a couple of things like this became out of date. Okay. Notice that that's still Euclidean geometry. It's just four-dimensional Euclidean geometry. But it's Euclidean geometry that's perhaps more relevant to today's world than the world in which Euclidean geometry was relevant. In the days when Euclidean geometry was coming out, the world was very Euclidean, in part because the only engineering that was available was based on the mathematics that was available. Today, it's very different. Now, Tony Robbins, and as I've put a little remark in here, you might say, well, it's just art. That means you can get a sense of it, you can get a human understanding of complexity in the real world. But is that really, do you need mathematics for that? Well, in a sense, yes, because since you're trying to understand something that is so complex, the mathematics at least gives you something reliable, a crutch to lean on in order to make those understandings. But you are actually having to interpret those drawings as a human in order to understand the complexity. However, I took his idea, having worked on that series, I sort of looked at his work. A few years later, shortly after 9/11, when I was working for the Defense Department, I actually took his ideas and built them into a tool on a Defense Department project. This was a project actually done for the US Army. And the mission was, or at least my job was, they were doing these very detailed special ops, and that's part of Baghdad. It was a historical mission. That was one of the ones we used for training. And the idea was they would have these special ops group going into Baghdad to just sort of, as they nicely put it, take out terrorist cells before they could do any damage. But whatever you might read to the contrary, they were certainly very cautious about collateral damage. They didn't want to kill people that were living nearby. They didn't want the soldiers to be killed. They wanted to be, as they called it, very surgical. And so they brought in a whole bunch of people around the country. I was just one of many that were brought in to do these, to see if we could develop tools that would help them to be much more, I mean, basically to save lives. That's how I argued it for myself. It was, you were saving the troops' lives. You were saving the lives of the innocent people living around. Okay. And so what I was supposed to do was say, can you take the traditional planning tools, which looked a little bit like that. There's an aerial view, which can be zoomed in from a satellite. You can zoom in to incredible accuracy, within 2 or 3 feet accuracy. Can we add to that a visualization of the other complexity that you can't see? The communications, the munitions, the various activities that are going on. So I did something just like Tony Robbins. I developed a geometrical model of all of the stuff that's going on in that scene that cannot be seen. The electronic stuff, the communications, the threats, all sorts of invisible things that are all part and parcel of a special ops operation. And there's no way you can sort of understand what, that's an interactive diagram on the right. The analyst can, or the commander can move it around and go forward and in different dimensions. There's all sorts of interconnectivity. It would be connected behind the screen to the visual scene, so you could reason from one to the other. And it was actually based on 3 pieces of some work that I'd been doing at Stanford. In fact, it was the work I came over to do at Stanford in the 80s, the late 80s when I first came to Stanford. It was to look at ways of visualizing information flow. And the reason I actually was asked to go on that project was because of some books I'd written. Logic and Information was one that came out in 1991. Then I took those tools and applied them in workforce design and workforce planning, and wrote a joint book called Language at Work. And then I wrote a more readable version of what we've been doing in a book called InfoSense that came out. And it was that work that formed the basis of that thing on the right. That's my equivalent of Tony Robbins' artwork, except this is not just art. This is about saving lives, locally saving 10s and 20s and 30s of lives, and globally, hopefully, saving millions of lives. So the stakes are kind of higher, but it was the same idea. It was trying to visualize complexity with a geometric model that was based on 15 years' work that had been done at Stanford that I was part of. So this stuff is powerful. It's very powerful. Okay, so there again is what's going on. We're taking that picture and we're applying it. In my case, it was that the Army example was special ops. That was a real-world application. The technical description was the Army. The Army has their own language. I had to learn it in order to sort of work with those guys. They have a very special language. So I had to learn all of the language that the military uses. And then my job was to take what they did, turn it into a mathematical language using the mathematics that had been developed at Stanford in the 80s and the 90s, and then do the mathematics to be able to sort of put that system together and feed it back into the world. By the way, I have no idea if that system was ever implemented. I didn't have security clearance, I wasn't military personnel, I just did an open project that was by no means secret, delivered the report and the ideas, and then I had no more access to it. So I have no idea whether they implemented that or somebody else's tool, because lots of other people were developing tools as well. Okay. I want to drill down one more step to say, how do we go around that triangle? How do we develop new mathematics? How do we develop a new model? Here, in 5 or 6 steps, is what happens. We first identify some pattern in the world. The first pattern that was identified was numerosity, sizes of collections. That gave rise to numbers. Then when we wanted to combine numbers, we developed arithmetic. Then there was patterns of visual space. That was what gave us geometry. We then study it. We try to be as precise as we can in studying that pattern. We then develop a notation to look at that pattern and to study it in detail, a notation that seems to fit the pattern itself. And then we use that notation to further the study. So in the case of numbers and counting, we develop various numeral systems. And sometimes when you develop a really good system, things move ahead quickly. And when our ancestors invented the Hindu-Arabic number system, then arithmetic became much easier to do and advanced much faster. In the case of geometry, we have the familiar geometric representations with diagrams and annotations on the diagrams. Okay. So you develop a notation, and then you use that notation to study it. The next step, historically, is you examine your assumptions, because the whole point of developing mathematical methods is to be more precise and to move into domains that we can't access immediately, to form conclusions, to make derivations, to take us beyond our existing knowledge. And so we might well find ourselves in a situation where the mathematics produces results that are counter to our intuitions. Happens all the time. We find something out in mathematics, we make a derivation, and the answer seems counterintuitive. Well, we need to know whether that counterintuitive answer needs to be corrected by changing the mathematics, or needs to be corrected by changing our intuitions. If we examine the assumptions, we formulate axioms, then we can check our derivations against the axioms. If the derivation is logically correct, then we know we need to update and upgrade our intuitions. So this step is an absolutely crucial one. You only need to do it once, but once you've done it, you can use it, but it's a crucial step. So we write down axioms. I went 2 at once. Studying the abstract pattern, then we just use the notion of truth by derivation to make sure that the mathematical ship is on course. And then we actually start to write down procedures, general procedures. We write down rules. For example, Newton was interested in the pattern of motions of the planets. A lot of the early work had been done by Kepler, who looked at the regularities of the pattern of the planets. And in order to take that into the mathematical realm, Newton invented calculus and wrote down a set of rules that allowed other people less talented than Newton in order to apply the methods of calculus. And most of us, when we go through our school and university education, we learn in mathematics, we learn the rules of calculus, and we find we can actually use calculus without understanding the deep ideas behind it. In fact, typically, it's only at the graduate level of mathematical study that mathematical students actually begin to understand calculus. It's actually quite deep to understand what's going on, but you don't need to understand it to use it because of these procedures. So the procedures that are written down allow it to be used by other people. And now we can just go out and apply it. Once calculus was invented, the procedures were written down, you can just buy a textbook where all the rules are laid out and start applying them. So now we've got an exportable cognitive technology that can be used. Okay, and that historically has been the way all of the branches of mathematics has arisen. Sometimes the real world we begin with is mathematics itself. Mathematics turns inward on itself and develops new mathematics. But eventually you can always unwrap it to an original application in the real world. Okay, let's focus on this little bit for a minute. We've got axioms, we've got proofs, and we've got procedures. That is what most people think of as mathematics. I'm going to call it mainstream mathematics because I'm looking at the whole thing as the mathematical enterprise. Okay. Axioms, proofs, and procedures. That's the bit we focus on in the schools. So a person who goes to school and goes through K through 12 and graduates from school with all of the mathematics that's required, they leave with that picture of mathematics. That's the picture they have. It's an important part of that big picture, but it's only a tiny part of that picture. So most people in the world actually don't have much understanding of mathematics because they've never seen it. That's the part that's changing now, because there was a good reason why the schools focused on that. But before I go into that, let me just say that the other bits are what you do to college. So if you go on and do a degree in mathematics at university, then you do the other parts. So if you graduate from university with a degree in pure mathematics, you're still in that box. For the most part, you're within that box. So that's the part that's familiar to people who've gone through a traditional mathematics education through to universities. And people think that typically that's what mathematics is. And historically, that's true. But it's not what it is today, and it's not what it's been for the last 25 years. Technically, it's not, officially, it's not what it was ever. But for very good reasons of having to do it and learn it, that was a perception that people formed about it. Okay, this whole thing is the mathematical method. All of the things in the box is the mathematical method. In the 21st century, which we are now in, I actually started giving this kind of talk before the 21st century, so this used to be a future-looking talk. Now, 21st century, we've already been in it for several years. Now we can actually go back and use mathematics with a wide-angle lens rather than the narrow focus. Most of today's real-world math problems actually do require that kind of approach. If you've got a problem today for which mathematics is required, it's probably required because it's a complex problem. If it's not a complex problem, then, I mean, there's so much mathematics available that if you can simply go into a problem and apply something that's known, the problem's essentially already been solved. The ones for which you really need to use mathematics are almost all now very complex ones that require very complex approaches, multidisciplinary approaches. The days when people could solve mathematical problems for real-world application on their own, by and large, are long gone. Not exclusively, but by and large. And even then, when you do need to use mathematics, we've got all of this stuff in the cloud, and much of it for free, that will actually do the mathematics for us. All of the procedures get done for us, which means the way people use mathematics today is one of the things they need to do, is make use of all of those resources. To get a general sense of what's happened, for 2,000 or 3,000 years, you could think of doing mathematics like learning to play a musical instrument. You know, there were different kinds of mathematicians. There were analysts, there were algebraists, there were geometers, there were this, that, and the other, there were number theorists. Each one of those kinds of mathematicians was like an instrument in an orchestra. You had to become very good, and then if you needed other people, you would form a quartet or you would form an orchestra. But being a mathematician was very much like mastering a musical instrument. Today, all working professional mathematicians that work on real-world problems are conductors. We no longer play instruments, we conduct a whole orchestra, because all of those human musicians have been automated. What you need is a conductor to bring all of that power together, that computational power, and do mathematics. So it's gone from playing an instrument, a mathematical instrument, to conducting a mathematical orchestra. It's up mathematics to a whole bunch of people who have always thought that they were not mathematicians and could never make use of it. Okay. This is so different from the way mathematics was used in the world for thousands of years that many years ago, I mean like 15 or so years ago, I actually, and not uniquely, but I started using the phrase mathematical thinking to distinguish it. Because the word mathematics to most people means the stuff that you do in schools and universities. So that's already got an assumed name. So we needed a new name to distinguish it from that. And so we started talking about mathematical thinking. It eventually crept into the educational world as well. That mathematical thinking is the key, you know, it focuses on the fact that it's people thinking, that it's not these procedures and so forth. That's just a part of it. So the mathematical thinking is the most general human stuff. It's the big picture approach. So we can fade away some of that. The basic assumptions part, that was always specialist stuff. I mean, engineers, for example, you use mathematics all the time. Engineers almost never bothered to learn that thing. They didn't need to know about the proofs. They didn't need to know about the truths and things. They would just take the tool set. So that was always a very specialist part of mathematics. We do sometimes still need to do that. In looking at real-world problems, we do sometimes need to do that. In fact, I spent most of my time at Stanford after I came here doing precisely that, saying what kind of mathematics do we need to look at these new problems of the information age. So we do sometimes have to do that. But by and large, that's just for the people who are trying to develop the new tools. We almost never prove theorems, in large part because, for two reasons. One, we probably can't because these tools haven't been developed sufficiently precisely. And secondly, there's not much point because we're actually now, if we're dealing with these complex problems, there's not going to be a unique right or wrong answer. There's going to be an initial answer. There's a better answer. It's almost always now about optimization. Get a better solution, get a better solution, get a better solution. All of the major problems, almost all of them for which mathematics is applied. Not a unique solution. And it's about getting better and better solutions. So proving theorems is pointless. It just makes no sense. It happens occasionally, but by and large, no. We can get rid of the procedures things now, developing procedures, because most of the time we don't need to. Occasionally you do, and people like me are the ones that would be doing that. But most of the time, if we're working on a problem and we need to use a procedure, almost certainly that procedure is now available on your iPhone. Just doesn't get done anymore. You just don't do it. It takes, first of all, if your iPhone can do it faster than you can do it. It can do it without making mistakes. And you are limited to 2 or 3 variables. You can throw 1,000 variable problem at it, and your iPhone will give you the answer. I mean, not your iPhone, it's the stuff in the cloud. But it will give it to you for free. So the limitations of people where we struggle, we make mistakes, and we can only do equations with 2 or 3 variables, all of that just becomes pointless now. The systems can do it for us much faster. They can draw the graphs, they can do it all. In fact, the nail in the coffin for having to apply mathematical procedures was the release a few years ago of Wolfram Alpha. Actually, Wolfram was, his office for developing Wolfram Alpha, if I remember correctly, was on Ramona, just round the corner. So he was here in Palo Alto doing the Wolfram Alpha. I actually visited him at one point when he was doing it. So it actually began, like many things in the world, in Palo Alto. This, if you haven't used it, and there's a free version you can download, but you don't need to download it, you can get it through a browser in your iPhone or your Google phone or whatever it is. This is a very big application. Mathematics is just one of the things it does, but if you go to Wolfram Alpha Mathematics, there are many, many templates. You see a little empty box, and in that box there will be a formula or there'll be a procedure or something which you can edit. So if you need to do any mathematical procedure, what you do is you go onto Wolfram Alpha, you scroll through the boxes until you find a template that looks like the problem you have to solve, and then you just go through and edit the one that's there into your own problem. You hit the go, and within a fraction of a second, you've got the thing answered, a graph has been drawn, all the information's there, it provides the background. The whole thing is solved in a fraction of a second, to whatever degree of precision you want. So when Wolfram Alpha came out, it was so easy to use, and it was free, that people just stopped using the procedures. That was essentially when all of my mathematical knowledge that had given me a good career for 30 years became obsolete, because here was this little device that could do all of that stuff much better than I could and do it in a fraction of a second. Now, fortunately, I'd come out of that process with something that the machines cannot do and probably never will, which is the creative part of mathematics, which is what's now important in order to conduct that orchestra of mathematical instruments. The musicians have been put out of business. The conductors are still necessary. And there are other tools. In fact, actually I gave a continuing studies course at Stanford just before Christmas with a colleague, Gary Antonick, whose name will come up again in a minute. And in order to give that course, I actually sort of, to myself, thought about what are the tools I use and what order do I use them in? So I actually came up with a slide. I don't think I showed this to the students in that course, but I was actually working on this at the time. I actually put down a list of the tools that I use and the order in which I use them. And here they are. So this is how a professional mathematician today would typically, and this is mine, so other mathematicians will vary somewhat, but this is the kind of thing that people do today when they meet a problem and they're brought in to solve it as a mathematician. Okay. First thing you do is you use Google. You just look at the keywords in the problem and you just play around with keywords, because the chances are pretty high, if it's an important problem, several people, several groups around the world have probably looked at it, may have even solved it. So maybe 3 out of 4 problems are solved just by doing an initial Google search. You just find out what somebody else has done it, you look for the publication or you whatever, and there you are. You may need to, in order to understand what comes back from Google, it may mention that they were using something. It might say they're using some kind of optimization technique, they're using linear programming. It might mention some technique they were using that you don't know about. So step 2, you go to Wikipedia and you just type in the name of that procedure, and almost certainly you'll get several pages that tell you how it works. And for technical subjects like mathematics, Wikipedia is wickedly accurate and almost always up to date. So it's extremely powerful and up to date. So you can get pretty well everything you need in the case of background from Wikipedia. So one of the things you need to be able to do as a mathematician today is quickly master something new. Not because you're going to go into the details, but because you want to use tools that have been developed by those people. You might need to send an email. So you probably do need to send an email, maybe to the people whose names are referenced. Then you might just try it yourself using Wolfram Alpha. Then you might think, wait a minute, I need to know a little bit more about this technique called linear programming. What is linear programming? I think I might have had a course as an undergraduate. So you go into Google and you type linear programming, and it delivers several hundred 20-minute lectures on linear programming. So you find one that you like, and within 20 minutes you've had a quick lecture, a quick instruction on what linear programming is, so you know whether that technique is going to work for your problem. You might want to put some data into a spreadsheet just to get a sense of how this thing might work out. You might want to go into a more sophisticated tool, either to learn techniques or apply things, tools like MathWorks, MATLAB, that kind of thing. This is my slide. I've got a very good network of several hundred people around the world, so I use LinkedIn to connect to people that can give me detailed background if I need to, so I quickly tap into the world's knowledge. Just as coders, computer programmers, can answer a lot of questions by going into a resource called Stack Overflow, mathematicians have something called Math Overflow, which is where you go online, you type in a technical question, and usually within minutes, because this thing is global, someone will answer with a technical answer, so you can quickly get the answer. You then might want to start using a very sophisticated tool that Wolfram developed before Wolfram Alpha, called Mathematica. Mathematica is a tool that could pass any university math major final exam with at the very least a B+ and sometimes an A-. It just does the whole thing very accurately. And then there are other resources, Quora, where you could get sort of background information about things. Again, because I have a reasonably large following on Twitter, very occasionally, if I want to find out a quick answer to something, I'll put something on Twitter and someone will put a quick answer in. That's a quick way of getting information. And then there's one other tool. There's one other technology tool which I find I need to use sooner or later in this process. It's that one. That hasn't gone away. But you only need to use it quite well into the process, because there's no sense in reinventing the wheel. The skill that's being used here is the conductor's skill of being able to marshal all of the world's knowledge, all of the world's expertise, and take it and shape it to solve the problem that you need. At some point, you probably have to change things a little bit, and that's when the paper and pencil comes out. But it's quite late in the stage, usually. You can do an awful lot with those first few. So that's a very, very different way of working from the way we used to have to do it. Okay. So what's the key feature of mathematical thinking? What kind of thinking is being done? What are we actually doing when we do this? In one word, and it's nice that this is a Greek word. You know, those of us that came through the Western tradition, we always think of mathematics as Greek. So nice to have, of course it's not just Greek, it's all sorts of things. But the Western tradition, we think of it as beginning with Euclid's Elements, which is Greek. So it's nice that there's a Greek word, and it's the word heuristics. And in true form, if you can't remember exactly what heuristics means, and actually most of us have a general sense, but here's what the thing officially means, and this is again the world's consensus through Wikipedia. There's the Wikipedia definition of heuristics, and here's the key part. Practical method not guaranteed to be optimal or perfect, but sufficient for the immediate goals. If your job is to help UPS or FedEx find a more efficient way of routing packages around the world, you're first of all being asked to solve a problem which in practical senses doesn't have a unique solution. You're in problems that are technically known as MP complete or various answers of that. Things like the traveling salesman's problem. You're in a domain where theoretically there's an answer, but in practice there isn't a real unique answer. UPS doesn't want the best algorithm for routing packages. It wants an algorithm that's 5% better than FedEx's. And then FedEx wants to do the same. It's the same with Walmart. It's the same with Google. It's the same with United Airlines. The goal is to be 5% or even 0.5% better than the opposition. If you're Amazon, you want to be slightly faster than everybody else. You know, Amazon's goal now is that everyone should get their package delivered within 2 hours or whatever it is. You don't solve the problem first of all. You find a solution and then you iterate and refine it. Why do you do that? Because computation is unlimited and it's cheap. So why do anything else? Do the mathematics, run it on real data. You don't have to run it on toy data. You can throw the real data at it and see how it works with the real data. You're still thinking. You're doing a lot of creative thinking. If you weren't, this would not be something new. If you've been called in as a mathematician or someone who can apply mathematical methods, new thought is required. But it's new thought that takes advantage of everything that's been done. So this is the kind of thinking that's being done. Okay. So I'm going to say a little bit more about that. And this is a math talk, so you can bet that at some point I'm going to ask you to solve a math problem. That dreaded moment is coming up. This is a simple little problem. It's one of these little puzzles that you often see on sort of, where you don't quite see them in the little bit of slip of paper you get in the fortune cookies, but it's that kind of thing. It's a little puzzle thing that you can get in puzzle books. I'm going to give you this problem. It's a one-liner. It's about buying something. You know, what's the cost of something? Where you're buying something. Simple little problem. If I gave you enough time, you could all solve this and you could get it right. That's not the point. This is not about whether you can get it right. What I want to get at here is what do human beings do very, very, very well that machines don't? because it's pointless trying to teach ourselves to do something that a machine can do much better. So learning your multiplication tables up to the 30s, in England we only went up to 12s, is no longer an important skill. Now, knowing the number bonds is a different issue. There's a whole bunch of things you need to know, but being able to execute those algorithms is no longer important because you're just wasting your time because you're up against something faster. What we want to know is, in a world where all of that computation is done for us, what makes the best use of the human mind? So if we can understand the bits of mathematics that we are much, much better at than any machine, then put us together with a machine and a whole new world opens up for us. So the purpose of this question is, and I'm going to say the following, I'm going to give you the question and I want you to answer it as fast as you can. You don't have to tell anybody, you don't even have to write it down, but just remember your answer. Because, and the question I'm going to give you, something like 55 to 60% of people get it wrong. And they get it wrong because they are very, very smart. Because they are using things that the human brain does well. And if we're aware of what the brain does well, then we can learn how to be mathematicians very effectively in this computationally rich world. Okay? So what I want you to do is solve the problem as quickly as you can. If you can just see the answer before you, good, that's fine. If you have to think about it a few minutes, think about it. But you're not going to get a few minutes, you're going to get a few seconds. So, and remember, the goal is to understand what it is that our brains do very, very well. And the way to do that is to see how they work when we just take off the blinkers and just let the brain do something fast. Okay, here's the problem. It's one sentence, well, it's a couple of sentences, very short. A bat and a ball costs $1.10. The bat costs $1 more than the ball. How much does the ball cost on its own? Time's up. And you don't have to tell me the answer. Okay? Because now we're going to look at what you did. With a small group, we'd sort of do something different. We'd get people to sort of give their answers and we'd count how many people got it. But let me begin by the answer that most people, the majority of people get. And they get it because this is what the brain is really good at. And we need to look at that because that's where the future lies. So this is the first solution. The first thing is you see that word more. You read these things, and the moment you see the word more, especially if you've done lots of university exams, timed tests, you've developed a method for dealing with timed tests. You scan and you see the word more and you say subtract. It's a subtraction problem. If it's a subtraction problem, you're going to have to subtract one number from another. You've got two numbers there, $1.10 and $1. The answer is going to be positive, so you're surely going to subtract the smaller one from the bigger one. So you do that, and you get the answer 10 cents, which is very, very smart, but very, very wrong. Okay? That's a heuristic. It's fast. It's unbelievably fast. Computers don't do that. Computers would have to, first of all, be able to parse the sentence. I mean, they can do it, and you could write a program that does it fast. But given that these things could come in all sorts of linguistic packaging, you're in something that human beings are much better at. Just large-scale pattern recognition, recognizing what the most important word is. The word more, in this context, is the one that jumps out of the page, and then you look at the two numbers. So you haven't done any calculation, really. You've just sort of said $1 and $1.10. That's not really calculating. You just know what the answer is. So it's a heuristic, it's fast, and it usually works. This question has been formulated in a way that is unfair because it's a very unusual one for which the heuristic doesn't work. And that's typical of heuristics. So if you got this one right, if you got this one wrong this way, you know, give yourself a pat on the back because your brain is doing the right kind of thing. It's been very smart. It avoided doing something kind of tedious. It avoided this. Because here's the method we were all taught in school. We'll use algebra. We'll say let x be the cost of the bat, because that's what we're trying to find. Or the ball is what we're trying to find. So let y be the cost of the ball. So those are the two things. I guess I'll do x and y in the order of the first sentence. You know that x plus y is $1.10. You know that the bat is $1 more than the ball, so x is y plus 1. So you eliminate x, you go through the process, and you get the answer 5 cents, which is correct. So that's a procedure. It's slow. But it does always work. Okay. And most of us spent many years learning how to do that. And people have been learning how to do that since the 9th century when algebra was invented by Al-Khwarizmi in Baghdad. And interestingly enough, it was developed to be more efficient. It was a way of scaling up arithmetic. The Arabic and Persian-speaking traders were developing modern trading methods at scale, and so they wanted an efficient way to do the arithmetic calculations that were repeated and many times with small changes. So they took algebra, they took arithmetic, put variables in, and they developed what we call algebra from the Arabic phrase al-jabra. So it was originally developed for efficiency, and it's not efficient. It was more efficient than doing arithmetic lots and lots of times. But it is accurate. It's accurate. And it's only accurate actually with 2 or 3 variables. If you've got a lot of variables, it becomes kind of impossible without some kind of technological aid. But that's the method we learned. Procedure, slow, and always works. And the reason we all learnt this at school was for thousands of years, there was no other way of doing these kinds of things. There were no machines to do them. You know, lots of other things in the world became eliminated with technology, but mathematics didn't. If you wanted mathematics, you could only do it yourself. We're getting close for time? Yeah, I'm almost there. Yeah, okay. Solution 3. Now we're done. Okay? You do this. You say, I want to find, it's about the ball. So what's the cost of the ball? You have in your mind a sense of what the cost of the ball is. You know that the bat is $1 more than the ball. So you have this general sense about the cost of the ball. You have a sense of the cost of the bat, which is the ball plus another $1's worth. And now you just look at this and you say, altogether, that's $1.10. So you've got cost $1. It adds up to $1.10. So without doing any calculation, you just read off in your mind that it's 5 cents. That is a heuristic, it's fast, and it always works. That is the kind of heuristics we need to go for. It's not to do with the symbols, it's to go to the concepts behind them. And this is the way pretty well all mathematicians work today. That's typically known as rigorous thinking, that's pre-rigorous thinking, and that's known as post-rigorous thinking. That terminology is actually due to an Australian mathematician, one of the best mathematicians in the world, Terry Tao at UCLA. He wrote a blog a year or so ago about this, pointing out that this is in fact how modern-day pure mathematicians do mathematics as well anyway. That this is how all mathematics is done. It's through heuristics. So the goal of today's education has to be developing that. How do you get there? Practice, practice, practice. No way of getting away from that. But machines do the accuracy. You don't have to be accurate. The machines will provide the accuracy. You have to do what the machines don't do, provide the understanding. Heuristics are essentially human things. So that means we should now be teaching all of the same old stuff, because that's still important, but in a very different way. Because what we need to do now is teach for understanding, not for execution. Execution is done for us. To teach for understanding, you've got to do it a different way. When you do that, you can actually apply it by learning on real problems. I actually taught a high school class at Nueva School down in San Mateo in January. In 6 hours, 15 kids, middle and high school level, reverse engineered UPS's scheduling algorithm. And they got it right. I was helping them, but they solved it. If you can reverse engineer one of the most valuable algorithms in the world in 6 hours, you can do almost anything. It was the way of thinking that mattered. They didn't have to know all the procedures. And that is today's world. Content no longer matters. It's all about the thinking. And that's what people are good at. You don't have to learn a lot of stuff. You have to learn to think a different way, and that's exciting to do. when I wrote my book, Mathematical Thinking, I did focus on that because you have to go through that. You do have to go through the traditional mathematics, but in a very, very different way. Okay, there's my coordinates. Thank you.
All right, so now we can take questions, and if you raise your hand, I'm going to bring the microphone over to you.
Thanks very much. Very, very nice. But at some point, computers will also learn how to do heuristics, and they already do, right? In a way, AI is a way of doing heuristics.
Yeah, the goalposts move, but we will always stay at the front because we're creative human beings. I don't believe in this infinity point stuff. I don't believe what they do down the road. I don't think, I'm not a believer that AI will overtake us, but it will constantly accelerate us along the path.
Yeah.
But I think we always stay ahead because of the way the brain works. Yeah. Not that anybody knows the way the brain works, but we do know how computers work. Yeah.
So are you or anyone else developing a curriculum that schools can actually use to do this kind of teaching of mathematics?
It was done. It's called the Common Core. It's not a curriculum. The Common Core laid out the principles behind this kind of education. The reason we have all of the issues about the Common Core is there was no way of testing. They were trying to take the Common Core, which was a good idea, put it into the schools, and the systemic system requires standardized testing, and there were no standardized tests available that could test that kind of thing, and that's going to take some time to do. So the principles are there. Implementing them is going to take a while, and there are issues you need to be careful about this, because we're talking about a revolutionary change in education. Now, it's one thing, the pros switching to this method, and we all did. Once these tools were available, we started using them, and everything changed. You know, no engineer does it. I mean, engineers started using Mathematica as soon as it was available, so did physicists. So we all made those change, but the people making the change had all got to be in those positions by studying mathematics the old way. So we knew that works for the people it works with. And we know that it excludes most people. There's good reason to believe we can teach a different way with more effects. But here's the problem. We can't perform global experiments on a whole generation of kids. So we can't revolutionarily change the education system. That would just be unethical. Even if we think we know how to do it, which we really don't, that would be a dangerous thing to do. So we can't make big changes. So education can only make minor changes and see if they're improved. So professionals made the switch quickly. Educationally, this has got to take generations to try and catch up, simply because we can't afford to do anything other than make relatively small changes. We know that if you teach the old ways, some people become very good at this kind of thinking. There's good reason to think that we can have a lot more people becoming good at the new kind of post-rigorous thinking. The question is, how much of the rigorous thinking do we need to go through? There's a very nice book by a guy called Daniel Willingham called Why Children Don't Like School, which looks at the reasons why kids get turned off in the math class or other classes, and it's all to do with the way the material is presented, the way we have to learn it. And we know that in order to become good at anything, you need lots of practice. You know, it's the old 10,000 hours sort of thing that keeps getting bandied about. To become good, you have to go through it. The goal now is to go through that process of rigorous thinking more quickly. How can we get people through that more quickly so they can get to the goal of heuristic thinking? Well, there are good ideas, there are lots of suggestions, but as I say, you can't just mandate that that's the way to do it, because it's necessity. The education system is going to take a long time. So the Common Core principles lay out the principles of what we want, so it's about understanding. I don't think that is controversial. What is controversial is how you go about doing it, and we don't even have good ways to measure the outcomes. So this is hard, and it will take time.
Yeah, because that actually leads to the other part of the question, which is that people have become so used to devices that if you go, let's say, to a retail situation, you know, people can't do basic calculations now. They're so dependent on that cashier and the register, or you ask them, oh, what about this coupon, that coupon, and they have to punch it in because they've kind of...
Yeah, so do I. Because what I have is if that answer is weird, so if the change that's given to me is less than $5 away, I don't even notice it. But boy, I notice if it's 25. So I have a system, you know, if you give me the change and it's out by a factor of $20 or more, a bell's going to go off. Because what I've got is number sense, and that's one of the main goals to develop. So the fact that people need to get a machine out to do the calculation, I don't think is important, because there's always, you know, throw that machine away and get another one, it's only $20. So, but knowing when the machine's given a ridiculous answer is a very valuable skill, and that's the important one, and that's the kind of heuristics one. You know, I mean, Amazon doesn't care if your answer is a 7% improvement or a 7.5% improvement, but the difference between a 7% improvement and a 20% improvement is huge. So it's all about just incrementals and getting edges. So it's that general kind of thinking that's important. So I don't think it's important if it's frustrating if the cashier can't sort of wing it. You know, if the power goes out and they can't deal with it, it's very frustrating. But I don't think that's a big deal anymore. But the other thinking is, and you know, for some people, $100 might be the fact. For me, I'm a college professor type guy, so $25 is when I get to worry about it. But I can recognize that just like that, and that's the human skill. Yeah, so I guess we need to bring someone at the back with a mic.
Yes. So is there a way to integrate this post-rigorous thinking combined with practice and eliminate the total procedural pre-rigorous thinking right from the beginning?
That's a research question. I mentioned that book by Willingham. If you look at everything that's been studied about people who develop high levels of skill, it's actually by lots of practice in the routine approach, rigorous thinking. So we've got a lot of evidence that suggests you cannot eliminate the rigorous thinking stage. In fact, we've got a lot of evidence that suggests you need a lot of rigorous thinking to get to the post-rigorous thinking. The question is, are you wasting your time spinning your wheels at that stage or not? For example, I would make a fairly confident claim that you're not going to become good unless you can learn what it's like to invert a 2x2 matrix and invert a 3x3 matrix. I don't see any reason why anyone should ever by hand invert a 4x4 matrix, which I had to do as an undergraduate. In fact, I had questions on my exams with 5x5s. It was routine and boring, and yes, it made me sort of look at how the determinants all nest, etc. But by the time I'd learned how to invert a 2x2 matrix and a 3x3 matrix, conceptually, I knew what it meant to invert a matrix and what it meant in terms of the geometry and so forth. And so I would say we can say, be very good at inverting 2x2 matrices, get the right answer, be able to invert a 3x3 matrix and maybe make some arithmetical slips, doesn't matter, and don't worry about the rest, because in the real world, you'll use Wolfram Alpha to do it for you. So what we can do, I think, is eliminate the parts of practice that became tedious. And they had to then, because if you had a 4x4 matrix in your job, you had to do it yourself. So we had to learn those procedures. We don't have to learn them now to do them, but we do need to understand them. You know, it goes back to the question of what if the answer's wrong. You need to have a good sense to say, no, that can't be right. You know, I've just inverted a 3x5 matrix. You shouldn't be able to do that because they've got to be square. So there's all these things that you can sort of acquire. So I don't think we can get away from lots of rigorous thinking. I think that's part and parcel of becoming an expert. You know, you can't become a concert pianist without spending a lot of time just practice, even at the scales, right? I mean, I don't think mathematics is any different. You've just got to develop the neural pathways. Right?
I wonder whether or not you've seen a change in mindset and approach to these kinds of problems from the students now at Stanford who are entering Stanford at this time who've always had this thing in their pocket that have been able to allow them to do this.
Oh, You bet. I mentioned that school I gave us. This was Nueva School is one of these sort of very fancy magnet schools down in San Mateo, that sort of way. And they had this January program where they have these sort of mini courses. I went and did a 3-day course for 2 days a week, Monday, Tuesday, and Wednesday, 2 hours a day. And that was the one where we reverse engineered the UPS algorithm. And I just gave them shipping data for one package and said, that's it. Come up with the algorithm, and I'm the math consultant. If you ask me a question, I'll give you an answer, and I'll give you some advice and hints, but you have to come up with a solution. They worked together in teams of 3 to 5. They took that method immediately. That's the way they did it. They went onto Google first of all. Then they used other tools. They absolutely took to it like ducks to water, which is why in 6 hours, they'd got the thing. Without my expertise as a consultant, it might have taken them 3 months. They'd have gone down false avenues, they'd have done all sorts of things wrong. But motivated, they'd have done that within 3 months. They would have got it. They absolutely do solve the problems that way. I was in Serbia a couple of weeks ago giving a lecture, and I gave this kind of lecture. And then I just went to some of the classes and watched the kids working in the class. That's how they were doing it. Yeah, so they do it that way. They've got the tools, they're familiar with the tools. And I get emails from students all the time saying, can you help me with this problem? And there's a question. You know, if it's a homework problem, I say no, but why don't you look at this resource? But sometimes it's a good question. And I always reply to those because I think they're doing the smart thing. They've got a problem. This is not something they could find in any textbook, but they've got a device that can allow them to talk to this guy at Stanford. That's a smart method. And I give them an answer. I give them hints, actually. No. But yeah, they absolutely can do it that way because that's the way they work. So they may answer the question that I'm hesitant about how do we change the educational system. They may actually show us how to change the educational system. I wouldn't want them to do it without any assistance because we're playing with a dangerous game if we do that.
I'm wondering about the psychological component in bringing about this kind of change in thinking. And with one of the problems I heard with Common Core was that students would bring home these concepts and they try to talk to their parents and they're very excited about it, and the parents didn't have a clue what they were talking about. And it takes a lot of faith on the parents' part that this is good, and a lot of parents can't do that. No, it is kind of interesting. I've actually had conversations after I've given talks with engineers sometimes from the Valley, not surprising living here, and you know, they'll come to me and they'll sort of say things like that. And I'll say, okay, I said, you're an engineer, tell me how you go about solving a problem. And within 3 sentences, they stop and they think, I've just described the kind of thing my kid says they try to do. So, you know, that's what the good engineers do, because if an engineer didn't work that way, they'd be out of a job. So engineers do have to work that way. And so the irony was that most of the engineers that wrote those things on Facebook were actually arguing against a method that was modeled on what they do professionally every day in favor of something that used to be done when we had to do these things by hand. Looking back, and I know a couple of people involved in developing the Common Core, looking back, it was sort of inevitable that was going to happen because this is a huge change. And those of us in the business, we've been living like this for 20 years now. People in the tech world have as well. It's the same with writing code. You know, in my day, writing code was like, you know, it was Fortran and at most, Pascal was the highest level language you ever did. It was writing commands. You know, my game company, we have a guy who writes the games. I open up the thing and I have no idea where the program is. You know, there's about 60 files with connections and links. And there's no actual program as far as I can see. And I have no idea how it works, but he thinks about it holistically. I've talked with him and it's very different. So the people that write code are very, very different in a different approach. So those of us that think of code as writing commands, occasionally you do have to do that, but most of the time it's done very differently. So the kids coming out of the school system, they write code a different way, they go about these problem solving a different way. What we need to do in the business as education is find a way to guide them that allows them to do what they can do well. But it is, it's a worrying time. And and it's easy for me to say this, I was in the middle of all of this when it was going on, but, you know, post-school teachers teaching mathematics, first of all, they're overworked and underpaid, all of those things. They don't have time to keep up with it. And this is a revolutionary change. What would be required to do the kind of course I gave at Nueva is knowing enough about mathematical techniques that no matter what these kids came up with that they thought might be a good way of improving that algorithm, I need to be able to give them advice. You can't expect an average math teacher to do that because they haven't been trained that way. They were trained to do something different. They were trained to teach people how to do things that can now be done by machines. Well, the world has changed, but it's going to be a long time before we can change that. So it's even a different skill set. My guess is that most of the math teaching in a few years' time, beyond the sort of middle school level, will be retired engineers. Seriously, I think they're the people that can do this, because it's the method of doing it, the method of approaching it that's important. So I think, you know, probably half the people in this room may be retired engineers, in which case I think, you know, the sooner we can get you back in the school system, the better. Because it's those metacognitive skills. It's knowing how to solve problems. And the point is that's where mathematics is now. You know, as I say, it's conducting an orchestra. But there are still those questions about how we go as fast as possible through the rigorous thinking stage. That's not going to go away. I don't think there's any evidence to suggest that would go away. So we're not going to throw that out. We just have to try and be more efficient with it.
In your travels around the world, what countries do you see encouraging this way of thinking in education more?
I'm actually, through my Stanford research, I'm closely involved with the Finnish system. I've been an advisor for the Finnish education system research for many, many years now, since 2003. So I've spent a lot of time in Finland. I've been in Finnish classrooms. You know, Finland became famous because their students became #1 in the PISA rankings for mathematics, even though they have something like a 4-hour school day, essentially no testing, no exams, very low workload, no homework, lots of discussion time. If you talk to Finnish teachers and Finnish university people, and I do, you know, they'll complain about the system as well. You know, no one likes their own education system. But from my perspective, they are doing a lot of things right. In some of the things they're doing right without being conscious of doing it. So, and they definitely encourage that method. It's a sort of an open, explorative method. I'm not sure if it's mandated, but that's the way I've seen it done in the classrooms. I don't have access to the school system in Estonia, but I do go to Estonia a lot, and I talk with young people at college level, and they are unbelievably good at this kind of thinking. I mean, Estonia is just way out ahead of the rest of the world in many, many ways. So they are, sorry? China is still, well, I haven't spent a lot of time in China. The picture we have, and I have no reason to disbelieve it, is that it's a very traditional go through the old process way, in which case they're probably backing the wrong horse. But with a population that big, they can afford to back the wrong horse, especially if you're not worried about societal consequences. China, Singapore's an interesting case because they are extremely good in the results, but their system is a system that's got built-in obsolete. It's like buying an iPhone. Eventually you're going to have to sell it and buy a new one, right? And I think Singapore's in that. Right now they're doing fine, but eventually they're going to have to completely re-engineer it. You know, it'll be like when Apple moved to a Unix base, largely through accidents and Next computers, but Apple found itself having to go to Unix at just the right time. So, you know, Mac operating system from then on was streets ahead of Windows and always would be, because Windows was still locked in history and could no longer make that change. So the educational systems, some of whom are still good that use the old system, that's got built-in obsolescence, and its lifespan is pretty short now, a few decades. So the countries like Finland, I assume Estonia, but I really don't know the details of that. And some of the states in the United States, I mean, you know, Nueva School, That's a pretty forward-looking school. It was very exciting. And you see some of the kids that come into Stanford with new ways of doing things. It's there. I was in Serbia 2 weeks ago, and I gave a talk to the math department, but afterwards I was talking to a group of students in the robotics class. They were doing that all the time. They didn't waste time. They were actually trying to develop, essentially, driverless automobiles, but it was just they had a road system built in. They were doing little Lego automated things that were meant to drive along a road system. They didn't waste time trying to solve the problem, because I watched them doing it, and they said they'd got it to the point where, and then the instructor said, well, right, it's going to come up to a junction. The thing has to recognize a junction and turn left. So they made some changes to the code. It went down, it recognized a junction and turned right. So they said, oh, must be a sign error. Went back into the code, fixed it, it turned left. Next problem. They just built the thing. I guarantee that's what they're doing at Waymo with the Google cars. You just put it in, try it, because it's instant. They didn't waste time analyzing it. They got some code together, put it in, and it worked. That's the way. And if there's a problem for which it's not the way, and I'm sure there always will be, then someone like me will charge you a fat consulting fee to come and do it for you. You know, the world will never run out of people like me who love the mathematics. There never were many of us. We'll always be in need. But the world was where it was only people like me that could make a career in mathematics. That's gone. You need one of me, and then 50 of those people could do just fine, and you bring me in once a month to sort out the problem. That's different. But it's, you know, anyone that works for a large company knows that's how it works anyway. I don't know if we've got time. Does it?
If there were, how many people do you think would be mathematicians if they weren't told they were bad at math because they weren't able to do the procedure part of math?
Yeah, that sounds like most people's lives, actually. That was the tragedy was, looking back, until we had these systems, these electronic systems, the only way to get into mathematics was master the procedures. So the schools were right that they spent the entire K through 12 mastering the procedures. And the universities were right in spending the rest of 3 years doing the theory behind the procedures, because that was the only way to do it. We had to do it ourselves. There was no other way to do it. So the number of people who became successful in mathematics was always small, maybe 1-2%. There was always more people that loved mathematics and wanted to do nothing else. People like me, if we have a job, we were lucky, because coming out of the graduate school, maybe 5 or 6 people graduate in a PhD in mathematics. Maybe one of them gets a job and the others go and do something else. They go and design algorithms for UPS or whatever. So there's never going to be a shortage of the expert mathematicians. But these days, now we've cracked the idea of the procedures being done automatically, you can get into using mathematics just like those 15 kids at Nueva School did without doing the procedures. So suddenly, using mathematics to solve real-world problems has become wide open to lots of people. You've got to be a good creative thinker. You've got to be able to use the resources. You've got to be able to marshal things together and put them together in the right way. But you never do need to do those procedures. And if you get to the point, as I say, where the procedure you're trying to solve doesn't seem to be solvable by any of the tools, then you bring in someone like me. So we've shifted the goalposts in a way from saying to use mathematics, the only way is to master the procedures, which most people fail to do, to saying if you can successfully and intelligently and effectively use all of those resources and pull in someone who knows about them if you need to, then it's not clear if there's any limit. It could be that almost anybody who goes to university could end up using mathematics in the world. Certainly those 15 kids at Nueva School, any one of them I would have thought could have gone and got a job working from Amazon or UPS or FedEx building mathematical algorithms because they'd already demonstrated it in 6 hours. So I think it's wide open. And it's,
Okay, yeah, so we have time for one more question.
So, is there an effective way of combining the use of procedures early in the kids' educational process with other techniques that also integrate, I'll do practice for the post-rigorous type of thinking. Is there an effective way of combining them so on the one hand, you had the benefit of the procedures and the rigor of that and the benefit of this and combining them into one curriculum? Is there a way to create that curriculum?
Let me give a simple short answer, which means it's probably going to be messy at the edges. The answer would be yes, and you would use project-based learning. You would have people working on real problems which are interesting, using real data which is available, and the mathematics that comes in sooner or later, if it's a good problem, and an instructor can make that call early on. If it's a good problem, sooner or later, if they're doing a project, which may be a whole semester-long project, sooner or later, they're going to meet something that means some rigorous thinking involved. At that point, they're into the problem, they're excited, they're motivated, and they will dig down into it. With the Nueva School kids, halfway through the second 2-hour period, enough of them had come across the idea that they needed to use this thing called linear programming. So then I gave a mini talk on linear programming. Actually, what I did was I downloaded a video from YouTube. We looked at that, we talked about it. So at that point, when their whole procedural advancement, which they'd got involved in, because they'd spent the first 2 hours brainstorming how to do it, they'd got into the problem, they'd got a sense that they could solve it. They're then invested in the problem, and then they're faced with learning some rigorous thinking. How does this thing called linear programming work, which is a geometric model? And they looked at 2 dimensions, we talked about 3 dimensions, and then we sort of mentioned that there was this method that had been invented by this guy at Stanford, etc., to solve it. So they're invested, they meet it, and then of their own volition, they're motivated to spend probably several hours one evening between classes looking at the details. I guarantee that they now fully understand linear programming much better than I did as an undergraduate because they got it in the context of a problem, they could see where it came from, where it led to, and they did the rigorous thinking. So it comes up, it inevitably comes up with a well-chosen problem, and almost any real-world problem that's meaningful is going to be well-chosen. And so project-based learning does do that. This is why I think the only people that you could do to teach it would be retired engineers, because they've done that all their lives. And new problems come in, the boss has said we're working on this, and they spend the next 3 weeks figuring out what the basic ideas were, and then they use all the metacognitive skills and do it. So we know that method works because people do that in their everyday lives all the time. What the technology does, and this is one way of looking at what the technology does, is allows us to take into the schools, at the very least the high schools, the kind of work practices that people use in the workplace anyway. Because you don't need to have the procedural mastery to start doing it anymore. You couldn't do that before, because the only way to solve the problem was to hand solve the equations. That's done, so you can apply the methods that people use in the everyday world. So, in a sense, the modern workplace demonstrates that the method works. But the only people that could teach that at the moment would be the people who've been using that professionally. So I think there's a great future for retired engineers. You know, what did they say? Snow on the top, fire in the belly, or something. Yeah. You know, when your hair turns silver, but you're still mentally active. Got a room full of people like that. But I think that's how it will happen. I don't see how it could happen, but I still think it's a very exciting time for mathematics because you don't have to go through that narrow procedural path to be able to do stuff. Okay, thanks.
Wow. Yeah, thank you so much, Keith, for this great talk. And you get the famous Cafe Cymac also. Thank you. Yeah, thanks everyone for coming. As usual, we'll have the registration opening up tonight for our next month event, and that's going to be about artificial intelligence. So we're happy to welcome you next month, and also on Monday for our birthday celebration. So once you log into Eventbrite, make sure to register for that as well. And have a nice evening. Thanks for coming.